Word. Let me share screen. I want to make a few last comments about this handout. The stuff at the end here about matrix multiplication via function composition is cool, but we'll come back to it. It's not, there's a section of the book where they talk about matrix multiplication, and I think it's the most natural way to define matrix multiplication, but we'll come back to that. What I wanted to say today, just a few last comments about linearity, because we have this definition of linear transformation, right? Is that this sort of like preserving addition and scaling, or preserving linear combinations? And I had you check, that these were nonlinear. And this one is kind of obvious because there's a square and there's a sign, and there's two variables multiplied together. But this one I think is less obvious, that it doesn't satisfy this definition. I mean, you can check that it doesn't satisfy the definition, right? Like if you have +7s, basically if you have a +7 in here versus a +7 in here and a +7 in here, then you get a +14 on the right. And so that's why it sort of breaks down. You get a +14 on the right and you get a +7 on the left. And so you get these things not matching up. But it really doesn't, it sort of goes against our notion of what linear means, like we're used to linear, like we're used to this being linear, quote unquote linear. So maybe just to write something down, so some last comments, some last general comments about linear transformations. Yeah, so I guess my first comment is that it's a really restrictive. So linearity in the sense of linear algebra, in the sense of linear algebra, is quite restrictive. So like, I think I sort of was saying this to some groups last time, that y equals mx plus b is not linear if b is not 0 in the linear algebra sense. All linear things are supposed to sort of pass to the origin. And in particular, if you just think about a linear transformation, like you can think about, you can think of y equals mx as a linear transformation t from R1 to R1, right? So t of x is mx. And so it's like M is like a 1-by-1 matrix. Kind of a goofy thing to think about, but you can think of M as a 1-by-1 matrix, like M is M, a 1-by-1 matrix. But that's the thing, is you can't do the plus b directly as a matrix. There is a way actually to get translation. So the M is just a scaling factor, and we can do scalings by linear transformations. The plus b actually shifts the thing and moves it, which is called a translation. It's like the plus b moves the line up. That's called a translation. And it turns out that you can't do translations with matrices unless you can do it if you go up a dimension. I'll show you that later in the semester, but it's kind of interesting. So there is a way to do it going up a dimension. But anyways, so that's kind of the thing, is like the b, not like, it's just weird. It's like we need things to go through the origin. Okay, so just keep that in mind. Like if you're going to do a transformation, linear transformation from 1 to 1, from R1 to R1, it has to be of this form. So it has to just be constant times x, no plus b. Okay. Okay. That's the first comment. The second comment is about these pictures that we had in number 7, where I was sort of saying like, because of linearity, if you draw t of I and t of j, so t of I here is 2, 1, and t of j is -1, 1. So maybe I'll Let me just do it over here. Maybe I'll just draw a picture. So, linear transformations geometrically. Trying to come up with a abbreviation for transformation geometrically. So for example, we had T of x1, x2 is 2, 1, minus 1, 1 times x1, x2. And so T of 1, 0, I'll just draw something kind of schematic here. It's not going to be perfect. Okay, so like T of I, T of 1, 0 is right there, right? 2, 1. That's T of I. T of j is negative 1, 1 is right there. And so for example, you can think about what T of I plus j is. Because of linearity, it's going to be the other side of this parallelogram right there, right? That's going to be T of I plus j, the tip of it. And then you can sort of do this extension. So let me see if I can do what he was doing. The dotted line thing. Oh, so I can't do it straight. Oh, she's gonna. You want her to come show me up? It's a skill. I had a student teach me a few years ago because I couldn't do it for a long time. But basically, you turn the square grid into this parallelogram grid is the point, right? Like you end up getting all these points. So like this point right here is the tip of T of 3i plus j, because I go 3 T of i's plus 1 T of j, right? And this point right here would be T of I minus 2j, right? Because I go 1 I and 2 j's that way, and so on. This point right here is T of minus I minus j. So it turns the square grid that you have, just the IJ grid that you have, into this like parallelogram grid. Yeah. Yeah, that's right. And so actually, that's a good point. This is really the codomain copy of the plane. This is the like y1, y2 plane. This is y1, y2. Right. So in the x1, x2 plane, you just get the square grid like this from the ij, the combinations of I and j. And here you get this parallelogram grid. So it converts square grid into parallelogram grid. Grid. And another, so a way that people describe linear transformations is that they take parallel and equally spaced lines and map them to parallel and equally spaced lines. And also it has to take the origin to the origin, right? So geometrically, if I want to write that down, geometrically, a linear transformation T maps the origin to the origin. It fixes the origin. And it preserves, I should say. We should say preserves. Because it preserves addition and scaling, but it also preserves the origin, and it preserves parallel and equally spaced lines, meaning, because right, you have the square grid, which is all these parallel and equally spaced lines, and then it turns it into this parallelogram grid, which is a bunch of parallel and equally spaced lines. It doesn't preserve angles or distances even, it doesn't preserve distances. The distances can get changed. But it does preserve parallel and equally spaced lines. And really what I should do is show you, I really keep meaning to assign these 3 blue 1 round videos, or even videos I've made. Algebra. Because he has these pictures of this, like where's on YouTube? Why aren't you giving me YouTube results? Oh, there you go. I guess I can just do that. Oh wait. I haven't figured out how to make this not super loud. Sorry. I remember this coming up before where like it's like super loud. You can see what I was watching otherwise on my YouTube account. I love watching Conan clips, man. That's like my favorite. Volume. I don't know how to turn it. Oh, I guess that's true. Yeah, that's a good point. I was looking for like system volume. So here's the series. And so these videos are just beautiful. Like I really recommend watching them. Because these good quotes. I love that. I'm not going to play the whole thing, but I just want to mention, like, what does he talk about? Oh, here. What I was doing with the parallelogram grid, right? I was just drawing the tips of the vectors. So I'm trying to find out where he actually might be the next video that I want to look at. Yeah, sorry. Let me go to this one. So he talks about matrices as linear transformations, and here I think stuff like this. Okay. You can see I wrote the same thing. Okay, so this gets into the like matrix stuff. And actually, this is actually what we're going to do today, sort of, is some of this geometric linear transformations. But I just wanted to show you some of that, just because those pictures are much better than anything I can draw on the board, right? So, okay. Yeah, and that's what I wanted to say was about that handout. But then the next handout actually is where, let me get to the next handout. Geometry of linear transformations. Let me open this and share screen to show it. So there's some stuff we've skipped in some handouts that we're going to come back to, but I just want to go ahead and move on, bless you, to this one. Let me share screen. Yeah, so right, I mean, it's going to come down to, and I think if you watch that video, he says the same thing, like basically in 2 dimensions, wherever I and j go determine where everything goes, right? Like we saw there. But in general, with n dimensions, wherever the standard basis vectors go, because you can write everything in terms of the standard basis vectors. Remember, E1 means like the vector 1, 0, 0, 0, 0, 0, 0, and so on. So this is the generalization of I, j, and k to like more dimensions. But because of linearity, if you just know where these vectors go, then you know where everything goes. And in fact, what we already sort of saw is that the columns of the matrix are the the images of the standard basis vectors. Like the 2, 1 and the negative 1, 1 are where I and j get sent. And so in fact, there's this kind of cool thing that if you want to like, if you describe a transformation geometrically, although it has to be linear, then you can just, once you know what happens to the standard basis vectors, then you can just write down the matrix immediately and then write down the general formula immediately. So let's do this example. I'm basically gonna do this example of rotating the plane 90 degrees counterclockwise, and then I'm gonna just put you into groups and have you do just more and more examples. There's like, you can just try to come up with examples, like try to build the matrix for lots of different transformations. And to me, this is like fun. So let's just do this. So, yeah, so finding the matrix of a transformation described geometrically. Described geometrically. So the idea, like I just said, is you just see what happens to the standard basis vectors. Like once we know what t does to I and j and k, if we want to throw in third dimension, that determines all of t. And in particular, say we have a transformation like R2 to R2. Well, the matrix, you know, so it's T of X is AX, and the matrix is actually where A is actually just given by the first column is T of I, and the second column is T of J. Right? So all you got to do is know what happens to I and J, and that just gives you the whole matrix and then lets you determine the whole transformation. Right, so for example, counterclockwise rotation by 90 degrees. That is a linear transformation. It preserves, I guess, around the origin. I should say around the origin. Because it preserves the origin, and it does preserve parallel and equally spaced lines, right? It's rotating. It doesn't change the fact that parallel lines, equally spaced lines are parallel and equally spaced. And so all you do is you sort of say, okay, well, what happens to I and J? I just draw my domain and codomain copies. And here's I. Here's J. And rotate 90 degrees counterclockwise. There's T of I, and there's T of J, right? So once you determine these, so this is the vector 0, 1, right? And this is the vector -1, 0. And so I guess what I'm saying is the matrix for this transformation, this first column will be 0, 1, and its second column will be -1, 0, which you can see on screen, but I'll write that down. So that's just the game. If you want to find the matrix for transformation, you just have to do this, and then you can find the formula. Write down what I just said. So we can write down A. So A is the matrix whose first column is 0, 1, and whose second column is -1, 0. And then T of x1, x2 equals A equals this matrix 0, 1, -1, 0 times x1, x2, which you can either do with the dot producty thing, row dot column, or you can do as x1 times the first column plus x2 times the second column. And that really just becomes -x2, x1, right? And so now you actually have a formula for rotation by 90 degrees. Does that make sense? And you can check this, by the way, like, does this make sense? Like, if I start with a point that's like here, like x1, x2. So that's over x1 up x2. And I rotate that by 90 degrees. You see what happens at that point? Like, it's kind of like rotating this whole triangle 90 degrees. It becomes like this, right? And this is -x2 now. This is x1. So this is the point -x2, x1, which is exactly what that transformation says. So you can sort of verify it for this specific case. But if you wanted rotation by 60 degrees, it's actually not that much harder. If you can just write down where I and J go, then you can get a full formula for how you'd rotate vectors by 60 degrees. Makes sense? Probably also, by the way, is like how all video animation and gaming works with this kind of stuff. So there's reasons why it's worth knowing. Yeah. Okay, so this just kind of verifies that formula makes sense. For more complicated stuff, it'd be harder to write down the general formula. So yeah, what I really want you to do is just start doing from number 2. They get hard. 2 and 3 and 4 and 5 aren't bad, and then you start getting to general rotations where you have to use cosines and sines and stuff, and general projections and reflections. Oh yeah, number 3. You have to draw some triangle geometry and stuff and try to figure out. But then like 4 through 7 are not bad, and then 9 and 10 get more tricky. So really, we could spend the rest of class just doing this. So groups, shall we? All right. let's do groups. I'll pause the recording and we'll see how it goes. Maybe I'll come back and make sure we all get the rotation matrix and maybe we'll start looking at the projections. But all right.